Hello, my name is Christopher Y. Tunick, and today I'm going to be doing a video on DNA replication and the process that involves within it. I'll be using a diagram that's included with this class. However, those viewing will probably not be able to view it unless they're part of the class, or of course the teacher viewing this assignment. So just keep that in mind. But it's relatively just a standard look at DNA replication and the separation of DNA. So I'm going to take a look at the picture and go off of it. So, and we'll also kind of go over the steps. So, in DNA replication, first, DNA helicase is going to go and unwind the double helix of DNA. So it's basically going to split that zipper into a fork. So you're normally going to have like almost imagine like a jacket on a zipper, how it's all kind of, just zippered up and connected. Well, DNA helicase is your zipper pulling it down and almost separating your DNA into two different strands effectively. Doesn't really look like how my fingers did, but you get the general idea. Now, because it's split, we want to make sure that the DNA doesn't sort of recombine together before we actually do the DNA replication. Because without check, the DNA will just recombine back together and we failed. So in order to prevent that, we'll have these single-stranded proteins being placed along the strands of DNA, which will basically prevent them from being connected back together and rebonded too early. And then from there, we'll have this, do quick pronunciation because I always mess this one up. I always miss one. Topoisomerase, I think that is. Don't quote me. I always mess that one pronunciation up. So topoisomerase is basically gonna prevent the DNA from excessive coiling. So excessive coiling or supercoiling would be like really good when we're doing like cell division, how we have to really tighten and pack up our cells and really make them real tight and small. But in terms of DNA replication, we want to make sure that our DNA is very like unwound and stretched out so we can do our proper DNA replication. So topoisomerase basically prevents it from doing that and bundling up too tight, and it basically rejoins the DNA in like a much more relaxed and calm manner. So it's not that jumbled mess that we normally see during cell division. So from there, DNA primase is going to start creating RNA primers along the basically along the DNA, and it's always going to they're going to be placed from a I want to say it's 5 to 3 or 3 to 5. I want to say 3 to 5 direction on both strands. From there, DNA polymerase. I think I'm getting that right. DNA polymerase is basically going to create that like new strand of DNA along the split strands. So you'll almost kind of see how it kind of unzippers, and then it'll start almost recreating that zipper, but for each different strand. So you're basically you're replicating each strand and duplicating it. So, however, there is a noticeable difference when looking at the two strands. As you can see, the top one, if you're looking at this image, it of course unzippers, but then the DNA polymerase basically, after it goes, it's just a clean zipper, a clean replication, no problems. Oh yeah, sorry. I messed that up earlier with my my notes. DNA primase is going to move from 5 to 3, not 3 to 5. Sorry, 5 to 3. But back to our little diagram here. So on the top, our top strand, it's just a straight zipper, no problems there. But if we look to our bottom, what's happening is you can almost see little breaks where the DNA hasn't been created yet, that extra part. And the main problem with that is because the way that DNA polymerase works, and it's also due to the part that the way the zipper works. Now, based on the fact that polymerase is going to move in a 5 to 3 direction, I'm able to just look at this diagram and immediately tell what kind or which strand is going to be our leading strand and which strand is going to be our lagging strand. It's super easy to tell. The lagging strand is going to be on the bottom one. You can tell because that strand has breaks where the DNA hasn't replicated yet due to DNA polymerase only moving in that 5 to 3. And since the top strand is completely clean, I'm going to have to assume that that strand is moving from 5 to 3 as it's unzippering from DNA helicase, compared to the bottom strand, which would of course be the opposite, since DNA strands are going to be in opposite directions and they synthesize in opposite directions. The bottom one's going to be 3 to 5 as you move from left to right, kind of looking at it in the diagram. So that's why you have the bottom strand being your lagging strand because of those breaks, compared to the top strand, which is the leading strand, because it's just a clean, smooth replication along it. All right. So the piece, oh yeah, so on that lagging strand, as you can see, there's those little pieces of nucleotides. Now in the diagram, of course, because this is just for, simplicity's sake, under normal circumstances, these strands would be about 500, I want to say, to like 1,000 nucleotides long. Really small, of course, but super long. And those fragments of nucleotides, those like gaps that are there, those are called Okazaki fragments. So now we're going to be finally moving on to our final step of DNA replication. So once the new strands are finally replicated, you're going to have DNA ligase, which is going to need to go along that lagging strand, because as you can see at the top where you have your replication, it's perfectly clean. The way DNA polymerase moved from the 5 to 3, it's perfectly clean and perfectly new made strand of DNA. On our bottom strand though, not so much. We have our breaks, our Okazaki fragments, because of the 3 to 5 movement across the replication fork. So in order to get that fixed, here comes in DNA ligase, here to connect those Okazaki fragments to the new strands of DNA fragments that they're going to create from DNA polymerase, and basically create the 2 strands from the parents. Okie dokie. Well, that's about it. That's my overall understanding of DNA replication and how it works. Thank you so much for watching. I really appreciate it. And have a great day, all of you. Thank you so much. Bye-bye.